Okay, so in a different mini lecture, we discussed this idea that magnetic fields exert forces on charged particles and current carrying wires. Well, it turns out that this isn't the only end of the story. That's not just what's going on. This mini lecture is going to discuss how current carrying wires produce magnetic fields. Okay, so in this mini lecture, we're going to look at the magnetic fields that are generated from current carrying wires. Now, how did this get discovered? Well, if you have a current carrying wire and you take a compass is a way that we can detect magnetic fields. We talked about in the first introduction to magnetic fields how if you align a magnetic material, it will align with the field. And that's, of course, what a compass does. If you take a compass and you put it near a current carrying wire, the compass will align. It will move. It is experiencing a magnetic field. And so that magnetic field is coming from that current carrying wire. The magnetic field of a current carrying wire encircles the wire. So if I were looking at the wire coming out at me, okay, so cross section through the magnetic field, or excuse me, through the wire itself, the magnetic field encircles that wire. Okay. The direction of that magnetic field is if we're looking at the wire, whether it's going clockwise or counterclockwise, so counterclockwise in this direction, the wire, it could also go clockwise. That was not a good circle. Okay, so it can also go clockwise, depends on the direction of the current. Direction of the magnetic field depends on the direction of the current. So how do we get that direction? Well, we use the right hand rule again. Always using our right hand. And again, it's a little tricky when I'm on the light board because my right hand appears to look like it's a left hand from your end. But I want you to practice this. So if you put your thumb in the direction of the current, your thumb in the direction of the current, your fingers make the circle that surrounds that wire that is the magnetic field. And so if a magnetic field is moving clockwise, that tells us that the current in this plane is into the board. So I'll draw the current in that direction. Counterclockwise, it's as if your thumb is pointing at you. That tells us that the current is out of the board. All right, so put your thumb in the direction of the current. And this is the conventional current, like the one that we use going from a high potential to a low potential. Put thumb in the direction of the current. Your fingers curl in the shape of the field. All right. What about the strength of the magnetic field? What do we think the strength of the magnetic field might be dependent on? Well, if I have a really strong current, we might suspect that I get a stronger magnetic field, and you would be right. So if I increase the current, I increase the strength of that magnetic field. Furthermore, if I'm looking at this wire and the current is coming out, or the wire is coming out at me, the current is coming out at me, the further and further I get away from that wire, you might suspect that field strength to go down. So as I increase the distance, we call that a radius, the distance from the wire, then I decrease my magnetic field. Right? So if I increase my distance, I decrease my magnetic field. Now, we can put this relationship together, and there's certainly some constants of proportionality that we will introduce you to. If I put this relationship together, we find that the magnetic field due to a current carrying wire is equal to mu naught, I'll tell you what that constant is, over 2 pi times the current over the radius. So those relationships hold true. If I increase my current, I increase my magnetic field. If I increase my radius, I decrease my magnetic field. Now mu naught is what we call the permeability of free space. And it has magnitude of 4 pi times 10 to the minus 7th Teslas per coulomb times meters. So Tesla meters per coulomb, right? So I can do a quick unit analysis. I need the magnetic field to be in Teslas. Current, of course, is in amperes. Sorry, that should be Tesla per ampere. And R is in meters. So Tesla per ampere times meter. That gives us the strength of the magnetic field due to a current carrying wire. The direction is going to be dependent on that right-hand rule. So let's do an example, get ourselves comfortable with this equation. I'm going to pop up that example and erase the board while you take a peek at what that is. We're going to look at two parallel current carrying wires. They are, let me get rid of the title. They are a certain distance apart, 20 centimeters apart. I'm going to look at my question there on the computer. 20 centimeters apart. One is carrying a current of 5 amps. One is carrying a current of 7 amps. Those currents are in opposite directions to one another. And the question is, what is the strength and direction of the magnetic field in between them? All right. So we're going to identify what we have in our problem. When we think about the strength of the magnetic field, it's no different than when we've talked about the strength of an electric field. The magnetic field at a certain location in space is going to be the vector sum of the magnetic field generated by any of the wires that are in that space. And so to solve this problem, we need to look at the magnetic field generated by each individual wire in that space in between them, and then take the vector sum of those two individual magnetic fields. All right, so let's identify what we have going on. We have two parallel wires. They are 20 centimeters apart between the two. Okay. Wire number 1, the current for wire number 1 is equal to 5 amps. And that is out of the page. Okay, so I drew them parallel, but you can imagine them coming out of the page. The current for wire number 2 is 7 amps, and we'll say that is into the page. So current for wire 1 number 5, wire number 2 is 7. So let's look at the magnetic field from current 1. We have the equation from the magnetic field, mu sub naught over 2 pi times current 1 over the radius, R1. And then we're told that it is halfway in between. We want to know what is the magnetic field at this location between them. And so that radius is 10 centimeters from any one side. So R1 equals R2, which equals 0.10 meters, so half the distance. All right, so we get 4 pi times 10 to the minus 7 over 2 pi times the current of 5 amps divided by 0.1 meters for the magnetic field from current carrying wire 1 We get 1 times 10 to the minus 5th Tesla. And what direction is it? Well, it's going to be in the upward direction. So I did this as a kind of a side view, but we can imagine that if this is wire 1, it says that it is going out of the page. So wire 1 is out of the page. Wire 2 is into the page. If I put my thumb in the direction of the current out of the page and I curl, that tells me that the magnetic field due to 1 is pointing in that direction in between them. So in the upward direction if I draw a head-on view of it. Okay. So magnetic field from wire number 2, same equation, mu naught over 2 pi times I2 over R2. Okay, we're given all of those variables. We have 4 pi times 10 to the minus 7 over 2 pi times 7 amps over 0.1 meters. And we find the strength of the magnetic field for the second wire is 1.4 times 10 to the minus 5th Tesla. Now what's the direction of this wire? It's current, the direction of the magnetic field for this wire. So that's going into the page. So you take your right hand and put your thumb in the direction of into the page and curl your fingers around. We see for this magnetic field, it too is pointing in the upward direction. So they're both pointing in the upward direction. They're going to add vectorially, both in the upward direction. We get the overall magnetic field strength is B1 plus B2. That gives us 2.4 times 10 to the minus 5th Tesla in the upward direction. All right, so using this idea for a long straight wire, the magnetic field produced by a current being carried in that long straight wire. So just getting used to that equation. All right, now it turns out that this equation works specifically for a long straight wire. It doesn't work for everything, so we want to make sure we appreciate that that specifically works for a long straight wire. But there is a generalization that we can get. Any current carrying element, whether it's a long straight wire or a curvy one, any current carrying element produces a magnetic field. And if we look at very small distances along that wire at a space that that current carrying wire passes through, we look at tiny little areas, we start to get an integration around a line surrounding that current, and it leads to what's known as Ampere's law. And Ampere's law tells us the magnetic field on a path during a line integral for a current carrying wire that encloses that current. It is the line integral of B dot dl, and that gives us mu naught times that enclosed current. So we're not going to necessarily dive into Ampere's law and use it. We're going to kind of stick with our study of these kind of long straight wires, but we actually use Ampere's law to give us more information that we're going to look at in a little bit, things that have to do with the magnetic field and solenoids. And so I want to introduce you to that idea and recognize that yes, this is a special case. If we used Ampere's law on two long straight wires or on one long straight wire, we would get this particular equation. So it's that generalization. I just want you to be aware of it. So, current carrying wires produce magnetic fields. Now let's look at what happens when I put two of those wires next to each other. If they're creating a magnetic field, shouldn't they be influencing each other? Well, check the next video out to find out. Good job.